In this lesson today, we're looking at reviewing polynomial division and factor remainder theorem. Possibly at the end of the lesson, looking at factorizing and solving polynomials. So I'll start by reviewing polynomial division. Now, polynomial division, as we know, because this is a review, we're looking at hijacking that division algorithm. So let's say we've got 510 divided by 3. We know with that long division algorithm, we've got 510 dividing by 3. The process is as follows, that we start by taking that leading digit. So we take 5 and we divide by 3. So 5 divided by 3, we've got 1. Now we know that we've used 3 here. So we're going to remove that 3 that we've used and we're left with 2. So that 3 comes from looking at multiplying 3 by 1. So step 1 is always going to be the leading digit division. Step 2 is going to be subtract the product of the quotient and the divisor. 3 is bring down the next digit, and then 4 is repeat. Now we keep on repeating until there's no possible divisions remaining. Okay, so if I follow that, we've got 1, we bring down the 1, we've got 21 divided by 3, and we get 7. 7 by 3 is 21, so we subtract 21, and we get 0. We bring down 0, 0 divided by 3 is 0, so we end up with 170. Now, we hijack that, and when we're looking at polynomial division, we use the exact same approach. So we'll look at a couple of examples. So this first example, we're looking at a quadratic, x squared plus 9x plus 4, and we're dividing by x plus 1. Now, we're going to stick with the leading digit thing, so we're going to start by looking at x squared divided by x. So x squared divided by x is x. Now, we're going to have to subtract the product between the quotient, which is our answer, x, and the divisor, which is x plus 1. So we're looking really at going x multiplied by x plus 1, which gives us x squared plus x, and that's what we're subtracting. So subtract x squared plus x. Now it should be that this first one always ends up as 0, so x squared take x squared is 0. 9x take x is 8x. Now we'll bring down our plus 4, and we'll get ready to go again. So our new leading digit is 8x. 8x divided by x is 8. And we're going to subtract our quotient, which is 8, multiplied by the divisor, x plus 1. So we get 8x plus 8. So subtract 8x plus 8, and we're left with 0, and 4 subtract 8 is negative 4. So in this case, we've got a remainder, because we can't divide negative 4 by x plus 1, of negative 4. So our answer to this polynomial division is that it's a quotient, x plus 8, and negative 4 as a remainder over that x plus 1, because we haven't divided yet. Okay, that's our process basically, and really it's a matter of becoming fluent and practicing with that. So we'll look again. So here we've got the polynomial x cubed plus 4x squared plus 3x take 4, and we're dividing by a quadratic x squared plus 2x plus 1. So it's a little bit painful, but luckily we use leading digit, so it shouldn't be too difficult. So leading digit is x cubed and x squared. X cubed divided by x squared is x. And now we have to subtract the product of x and the divisor. So that's a quotient x, and the divisor is x squared plus 2x plus 1, which gives us x cubed plus 2x squared plus x. And so we're going to subtract that. We've got x cubed, 2x squared, and x. And when we do this subtraction, we get 0 here. 4x squared take 2x squared gives us 2x squared. 3x take x gives us 2x, And we'll bring down our negative 4. Ready to start again. 2x squared is our new leading digit. 2x squared divided by x squared is 2. And we're going to subtract our quotient, which is 2 multiplied by x squared plus 2x plus 1. And we get 2x squared, 4x, and 2. So we're subtracting 2x squared, 4x, and 2. So we're left with negative 2x, and negative 4 take 2 is negative 6. Now this will be a remainder because we can't divide a linear by a quadratic. So our remainder is negative 2x take 6. That means our answer is that it's x plus 2, and we've got negative 2x take 6 over our divisor, which is x squared plus 2x plus 1. So we got an answer of x plus 2, and we weren't able to divide negative 2x take 6 by our x squared plus 2x plus 1. All right, so we've got one more example. Now this one is important because we've got missing powers. When we have missing powers, we want to fill them in. So that means that we want to look at this as 2x to the power of 4 plus 0x cubed plus 0x squared plus 6x plus 11 over x take 2. Now when we do that, it means that we can keep track of it a little bit better. So 2x to the power of 4, 0x cubed, 0x squared, 6x and 11, and dividing by x take 2. Alright, so we'll start by looking at the leading digit. 2x to the power of 4 divided by x. So that gives us 2x cubed. I'm going to subtract 2x cubed multiplied by x take 2, which is 2x to the power of 4 take 4x cubed. So that's what we'll subtract here. 2x to the power of 4 take away 4x cubed. Now, this is where we have to be pretty careful. 2x to the power of 4 take 2x to the power of 4 is 0, that's good. 0 subtract negative, which makes that a plus. So 0x cubed plus 4x cubed gives us 4x cubed. And we'll bring down our 0x squared next to it. Here's our new leading digit. 4x cubed divided by x gives us 4x squared. We're going to subtract 4x squared multiplied by x take 2. So 4x squared multiplied by x take 2 gives us 4x cubed take 8x squared. So 4x cubed take 8x squared as our 0. And take away a negative makes it plus, so 0 plus 8 is 8x squared. We'll bring down our plus 6x. Right, next step we'll go again. Here's our new leading digit. 8x squared divided by x gives us 8x. And we're going to subtract 8x multiplied by x take 2, which is 8x squared take 16x. And that gives us 0. 6 take away negative, which is plus, so 6 plus 16 is 22x, and we'll bring down our plus 11. Alright, final step. 22x divided by x gives us 22, and we will subtract 22x take 44. So we end up here with 0 and 11 plus 44 is 55. So we end up with a remainder of 55. So that means our answer is that it's 2x cubed, 4x squared, 8x plus 22, plus 55 over x take 2. Okay, so as you can see, they start off nice and easy, and they build up in complexity, and this is a skill you really have to practice to get fluent at. Now, the second side of this is factor remainder theorem. The whole idea is that if we're dividing some polynomial, so let's say that's p of x, by some linear factor, so x take a, then we'll get some answer, some quotient, and we'll end up with the possibility of a remainder that's yet to be divided by the original thing. So that's really similar to the pattern that we've got there, right? We've got some polynomial divided by a linear factor, and we ended up with a quotient and some remainder over that same linear factor. Now, this is where it gets kind of cool. If we multiply everything by x take a, then we end up with p of x is equal to that quotient multiplied by that linear factor plus the remainder. So if we multiply by x take a and divide by x take a, it kind of cancels out. Now, in this scenario, if we let x equal a, so whatever that divisor is, that we end up with the polynomial with a subbed in, q of a take a plus r. Now, the secret here is that a take a is 0, and when we multiply by 0, it's gone. So we end up with p of a is equal to r. Now, this is remainder theorem, and that tells us if you sub in the value, then you'll end up getting the remainder. If we can get the remainder is equal to 0, then that is factor theorem. If that remainder is equal to 0, then it's factor theorem because that x take a must be a factor of the polynomial. So basically we're saying that it goes perfectly in. Now, we can use this pretty well. So we can say that if p of a is equal to 0, then x equals a is a solution or an x-intercept. And if x equals a is an x-intercept, then x take a is a factor. And that's what we're going to use from now on. So we can determine remainders, but we can also, at the same time, try to determine factors if we can find a scenario where we can sub in a value and get 0 as the outcome. All right, so let's look really quickly at some of the ones that we've already done. Now, because we're dividing by x plus 1, then that makes the a value that we're dealing with -1. So we're saying that we're going to let x be -1. So p of -1 is equal to, so we're subbing -1 into this original function here. So that's our p of x is equal to x squared plus 9x plus 4. So we've got -1 squared, 9 times -1 plus 4. Now what comes out of here will be a remainder for when we were dividing by that x plus 1. So we've got 1 take 9 plus 4. So we end up with -4. So our remainder is -4. So if we go back up, we've done this question before. There it is. So x squared plus 9x plus 4 divided by x plus 1. If we do that division, we end up with a remainder of -4. So we can see our remainder theorem here works. The remainder is -4. So it's really quick. If we want to find that remainder, we can do it much easier. So if we go back to this same example, and the goal now is to determine the remainder, we've got 2x to the power of 4 plus 6x plus 11 divided by x take 2. Remembering that this was quite a complex polynomial division, this is our x take a, that's our linear divisor. So if that x take 2, we can use x is equal to 2 as the value that we're going to sub in to that polynomial. So the polynomial is equal to 2x to the power of 4 plus 6x plus 11. And if we want to find that remainder when we're divided by x take 2, then it's as simple as substituting 2 in. So 2 multiplied by 2 to the power of 4, 6 times 2 plus 11. And we've got 32 plus 12 plus 11, and that's 55. So we end up with that division, a remainder of 55. If we go back up to that earlier example, we can see again that that is the same remainder we came up with when we did the whole polynomial division. Okay, so where this is nice, being able to determine remainders for these divisions, it's not overly useful when we start looking at solving and factorizing polynomials. What's important and what's useful when we start solving and factorizing polynomials is factor-remainder theorem. So when we get asked a question like this, where it's find the zeros, which means the solutions, then we're looking for all the scenarios where the remainder is 0. So all the ones that are true linear factors, or the ones that do have solutions. Okay, now there's 2 ways to do this. The best way is to find one solution and then divide by the associated factor, and then factorize the remainder, or factorize the remaining quotient. Okay, that's the best way. The other way is that you could use factor theorem for all of the linear factors. So find all solutions using factor theorem. Now this is problematic because we look at this and we cubic and we go, there must be 3 solutions, but it actually means that there could be 3 different solutions, there could be 2 solutions, or there could be 1 solution. So you have to be careful there, and this is probably not a good plan in most scenarios. So not a good plan in most scenarios. What I'll do is I'll use the other way for this one, and then we'll use the best way in the next example. So really the idea is that we start subbing in values. So 24 here, the only possible solutions are factors of 24, so we can look at positive, -1, positive, -2, 3, and so on. So let's start by looking at 1. So if we sub in 1, what do we get? We get 1, take 14 plus 24. We know that that's not 0, so that's no good to us. -1 is also similar, it's not going to work very well. So now we'll look at substituting in 2. So we've got 2 cubed, which is 8, 2 squared, which is 4, 14 times 2, 28, and then plus 24. So this one does equal 0. Now that tells us that x equals 2 is a solution, and therefore x take 2 is a factor. So great, we've got 1 of the 3. We can play around for a bit. Let's try 3. So if we put 3 in, 3 cubed is 27, 3 squared is 9, 14 times 3 is 42. Sorry, that's subtract 42. And then add 24. So this one's a little bit more complex. So we've got 51 and 51, so it does equal 0. So that means that x equals 3 is a solution, and x take 3 is a factor. So now we've got 2 out of the 3. Now we could play around all day. I know that the other one is -4. So if we put in -4, then we also end up with 0. Now I'm sure most of you can see the issues with taking this approach. It's a trial and error thing. You may be unlucky and try 10 different things. Also, you may make calculation errors. It's just a bit messy. So finding 1 is the best bet. In this case, though, we end up with x equals 4, and then x take 4 is a factor. So our solutions are x is equal to, that's a -4, and that therefore needs to be a +4. So our solutions are x equals 2, x equals 3, and x is equal to -4. And if we were trying to factorize, we could say p of x is equal to x take 2 x take 3, and x plus 4. So there's our fully factorized polynomial. All right. So I want to quickly talk about this process of factorizing or solving a polynomial. Basically, the best approach to take is find a linear factor. So if you think about what we just did there, it's looking at p of a and trying to let that equal 0. Once that's done, we can say, well, x is equal to a is a solution, and therefore x take a is a factor. So that's important. That's our first step. Once we've got that factor, we can divide the original polynomial by that factor. So that's what we've got here. Polynomial divided by the factor, and we get our answer. Now this works well because factor theorem, remainder is 0. There is no remainder here. So what's left over is a perfect polynomial. That polynomial can then be factorized. The idea is that this might be a quadratic. We can factorize that quadratic, and then we can set our final answer, which is that linear factor and the new linear factors that have been determined by factorizing that quotient. So let's look at this in practice. We're going to try to factorize. That's an important word. We want to determine its linear factors of this polynomial. So step 1 is that we want to find a solution. So using factor theorem, we're trying to get the remainder is equal to 0. So let's start by testing 1. When I sub 1 in, I get 2 plus 7 take 10 take 24. Not 0, that's no good. Let's try 2. So 2 times 2 cubed is 16. 7 times 4 is 28. I wrote 24, but I meant 28. 2 times 10, so subtract 20, subtract 24. So this ends up being 44, subtract 44. It is equal to 0, which means x equals 2 is a solution, and therefore x take 2 is a factor. And now I know that if I divide p of x by x take 2, I'm going to get that quotient, which hopefully I can factorize. So let's do our polynomial division. We've got 2x cubed plus 7x squared take 10x take 24. Dividing by x take 2. We've got leading digit division. And we've got 2x cubed divided by x gives me 2x squared. We'll subtract this product, 2x squared by x take 2, which gives me 2x cubed take 4x squared. This is a 0. And 7 take away negative 4 is 7 plus 4, which gives me 11x squared. We'll bring down our negative 10x, and now we can start again. This is my new leading term. 11x squared divided by x gives me 11x. We'll subtract this product of 11x and x take 2. So that gives us 11x squared and negative 22x. 11x squared take 11x squared is a 0. Negative 10 take away negative 22 is negative 10 plus 22. Gives me positive 12x. And I'll bring down this negative 24. All right, last step, leading term is 12x. 12x divided by x gives me 12. And then we can subtract 12 by x take 2, which is 12x take 24. Now I know I've done this right because this zeroes out completely. There's no remainder. So what we're saying now is that our polynomial can be rewritten as x take 2, that first linear factor, multiplied by this quotient, which is 2x squared plus 11x plus 12. Now our goal is we want to factorize this guy. So this is a quadratic, and we're good at this. AC is 24. B is 11. So it must be 8 times 3, 8 plus 3. And so my factorization here is, we've got 2x squared plus 8x plus 3x plus 12. Common factor for the first pair is 2x, so we're left with x plus 4, and then 3, and we're left with x plus 4. So my full factorization is x plus 4 and 2x plus 3. Now we can finish our factorization over here. Our first linear factor is x take 2. Second is x plus 4. And the remaining one is 2x plus 3. Now, if we wanted to solve this, that is when we let p of x be equal to 0, and we'd use null factor theorem, but because it only asks us to factorize, then this is our final answer. We'll put a big yay. All right, so that concludes the lesson. That's our last example. The questions that you'll be working through is more of this. So you can see the first set of questions are simply polynomial division. That gives you some practice there. Question 8 is very challenging, so good luck and have fun with that one. And then exercise 11, some long division, some factor theorem, remainder theorem, where they're asking you to find remainders. And then finally down here, we're asking you to fully factorize. And then we're looking at a complex unfamiliar. Okay, thank you very much for the lesson.